This is the eighth in a series of resources on integral calculus. We define the idea of an integral. We investigate the fundamental theorem of calculus and look at some basic rules for integrals. We explain the difference between definite and indefinite integrals, looking at a basic example. We consider using Riemann sums as a method for approximating a definite integral. We investigate the integrals for specific function forms, including polynomials and trigonometric functions. We will also look at substitution methods to simplify certain integrals. One additional form of substitution method is called integration by parts. Where does this method come from? Recall the product rule for finding derivatives. Suppose we have two differentiable functions, u and v. The derivative with respect to x of u multiplied by v is equal to u multiplied by the derivative of v with respect to x plus v multiplied by the derivative of u with respect to x. If we integrate both sides of the equation, the integral of the derivative with respect to x of the product is therefore the same as the integral of u multiplied by the derivative of v with respect to x plus the integral of v multiplied by the derivative of u with respect to x. Integrating the left side, we have u multiplied by v equal to the integral of u multiplied by the derivative of v with respect to x plus the integral of v multiplied by the derivative of u with respect to x. Rearranging, we have the integral of u multiplied by the derivative of v with respect to x equal to the product of u and v minus the integral of v multiplied by the derivative of u with respect to x. How does this formula help us? Some functions are impossible to integrate as written. If we can make strategic choices for u and dv, then we can complete the integral algebraically. But how exactly do we use this integration method? To use integration by parts, first we have to select our values for u and dv very carefully. After all, we want to make our integral simpler, not add complexity to it. Then we find the derivative of u with respect to x. We integrate dv. Now we have all our parts and we can plug into the formula. Find the remaining integral. Then simplify whatever we have remaining. Let's look at a couple of examples. Suppose we want to find the integral with respect to x of x multiplied by the cosine of x. When using integration by parts, we want to have the remaining integral be as simple as possible. This means we want to have the simplest choice possible for u, the function for which we find the derivative. With this example, we select x as the u and cosine of x, dx, as dv. Taking the derivative of our choice for u, we have the derivative of x equal to dx. Taking the integral of our selection for dv, we have the integral of cosine of x dx, which is sine of x. Plugging into the formula for integration by parts, we find that the integral of x cosine of x dx is equal to x multiplied by sine of x minus the integral of sine of x dx. We still need to find an integral. The integral of sine of x dx is negative cosine of x plus c. So we have x sine of x minus negative cosine of x plus c. Simplifying, we find that the integral of x cosine of x is equal to x sine of x plus cosine of x plus c. Let's look at one more example. Suppose we want to find the integral of x multiplied by e raised to the negative x power dx. This is another example of a function that cannot be integrated directly, but we can find the integral by parts. We choose to have u equal to x and dv equal to e to the negative x dx. The derivative of our choice for u, x, is dx. The integral of e to the negative x power with respect to x is negative e to the negative x. Now we can plug into the formula for integration by parts. We have the integral of x e to the negative x dx is equal to x multiplied by negative e to the negative x minus the integral with respect to x of negative e to the negative x. Finding the integral, we have the integral of x e to the negative x dx is negative x multiplied by e to the negative x power minus e to the negative x power plus c.